Okay, so this is the final lesson of solubility equilibrium. However, to be honest, usually in class, this would comprise 2 days at least. So what we're going to do is I'll just make one video, and as we're going through the video, I'll sort of stop when the different topics stop on the solubility equilibrium worksheet. So if you want to pause the video and then go on to the next kind, then you can certainly sort of do that, okay? And then the last section, the common ion effect, is often the most difficult, but really, to be honest, usually if we were in class, we would have had like 3 quizzes, and sometimes there's no quiz for common ion effect. So maybe that's why it just seems harder, okay? This is a super good lesson because it actually is, well, it's literally called applications, right? So it's applying what we've already done. And it's kind of cool to see. And again, thinking about things that we use, maybe sort of not took for granted, but like just qualitatively looked at whether precipitate forms or not. But there's actually a lot that goes into it. You can't just randomly mix 2 things together and expect a precipitate to form. Even what we did in grade 11, where we used the solubility chart and said whether it was soluble or insoluble, still requires a certain concentration. So we're going to look at that today. Okay, so predicting precipitation. So here again, we're going to do a trial product. It's called, or a trial value. It's called a product because, as you know, when we've been doing solubility equilibrium, then because the solid is always on the reactant side and we cross it out in the ice table, then all we're left with is multiplying the ions, right? There's no numerator or denominator in our fraction. Okay, so then similar to last section, K is the concentration of products over reactants, but again, no solids go in the equilibrium law. So then when we do Q, we calculate it exactly the same way and compare it to KSP. So we're going to do the same thing. Is Q too big? Is Q too small? Or is Q equal? And then we have one extra step this time. We'll still talk about whether it shifts forward or reverse or right or left, and then we'll talk about why, but then we'll also look at, does a precipitate form? So there's one extra little piece to these questions. Okay. Oh, please be kind about my highlights, all right? So if Q is equal to KSP, then the system is at equilibrium, which means, of course, in this section, a saturated solution, which means no more can be dissolved, but you can't see any precipitate. And then if Q is greater than KSP, then that means that the number is too big. So again, when you have a K at a Q, they're calculated the same way. It's products over reactants. So if the number is too big, then the bottom of the fraction needs to get bigger. Where are the reactants? They are on the left, okay? So that's what we would have done in the last section. Now we're going to add one more thing to it. So if more solid is produced, then you get a precipitate. You could also say that solubility is decreased. It means the same thing. So precipitate is a fancy word for solid. Technically, the solid formed in a chemical reaction and a double displacement reaction. We chemists love short forms, so I'm going to use the short form PPTE because precipitate is a long word. Okay, so then the same thing, when Q is too small, then the system needs to get larger, and in our fraction, the larger number needs to be, you want it to be at the top, which is the products. So it shifts right towards the products. It's exactly what we would have done last section. But now we're going to say, okay, so more ions are on the product side, which means that the solubility is going to increase, or more of it will dissolve because you have more ions. Okay. The one other tricky thing to this is you're going to be given numbers usually in scientific notation. So it can be a little bit frustrating to try to figure out which number is bigger and which number is smaller when you have scientific notation. Okay, so just be careful of that. So let's do an example. Consider a solution containing copper ions and chlorine ions, each at a concentration of 4.1 times 10 to negative 4. Will a precipitate form? So this question is similar to topic number 2. So if you want to, after this, pause and, or even example number 2 as well is like topic number 2, then you can pause and take care of those questions if you want to do that. Topic 3 is a little bit different. Okay, so we're given the KSP, so we're going to calculate Q and compare. So Q is copper and chloride ions. So this is even easier. It tells you what kind of ions you have. You don't even have to really worry about what it breaks apart into if you struggle with that. Plug in the numbers and you get 1.68 times 10 to the negative 7. Okay, so here, this is where when you're doing scientific notation, maybe this is going to be frustrating for you, but the negative 7 is the same on both sides, or in both numbers, sorry. So that means that you can just look at the coefficient here. This big number is called the coefficient. So that means the KSP is 1.9. That is bigger than Q. So Q is less than KSP, so that means if it's less than KSP, it needs to increase. If you have a fraction, how are you going to increase? You need to increase the top of the fraction. In our case, what's always at the top? Products. And specifically for solubility, products are always aqueous ions, so no precipitate. Okay, so Q less than KSP. That means the Q value needs to increase. How does it increase? You want to increase the top of the fraction, which is where the products are. And in our solubility case, products are always aqueous ions, which means no precipitate. Okay, so the next question is slightly different because it says, so this is also topic 2. This is a case where you're trying to figure out where you're just going to get precipitation to start. So you're given a KSP value and you're given concentration of one of the ions and you're asked to find the other one. So when you have a saturated solution, that means that no solid will dissolve. Any concentration above that value will make a precipitate. So if you were in my grade 11 class, we did a lab where we made a white solid dissolved, and then we got it to recrystallize. So even if you add one more little speck, you would have seen recrystallization, or it literally is it looked like snowflakes growing kind of when it recrystallized. Okay, so saturated solution, so if you no precipitate, everything's dissolving, then anything greater than that concentration will make a precipitate. So what we can do is use what we have and solve for the Cl minus, and then add a little statement. Okay, so here's the solubility equilibrium, which is also on the other slide. So KSP is silver and chloride for silver chloride. We are given the KSP and we're given the silver concentration, and you just solve. So you divide by 0.005 to get the chloride concentration. So if silver is 0.005 and chloride is 3.54 times 10 to the negative 8, that is going to be equal to KSP. So if you left your answer like this, it doesn't really answer the question. So what concentration is required to just begin precipitation? You want to say anything above these two concentrations. So whether you increase the silver or increased the chloride, it would make it shift to the left, and that would give a precipitate. Okay, so it says at 0.005 and 3.54 times 10 to the negative 8, then a saturated solution exists. Anything above these values will yield a precipitate. If you want to add more in there, you could, because the ions Simple, this should tell you, okay? If the concentration's too high, how does it go down? Shifts away from it. Okay, so now on to topic number 3. We're still determining whether a precipitate will form, but this question is a little bit different. So I believe if you printed the note off, you'll still have space to fill this in on the paper, unless you write enormous. But you can see here there are a lot more numbers. So we're still given a KSP value. That's important. We're told that the KSP is for CaSO4. But what we have here is a double displacement reaction. So it's saying 100 milliliters of 0.1 molar calcium chloride and 100 milliliters of 0.04 molar sodium sulfate are mixed. And this is basically how many reactions have you done that are double displacement in your life? So in your chemistry lives anyways, you have done this all the time. So again, when a grade 10 teacher comes to me and says, we want to, you do that testing ions lab with the dropper bottles. We need this to work. I have to figure out what concentration it is, not just is it going to make a precipitate or not. So there is a quantitative side to it as well. Okay. So yes, this is a double displacement reaction, and this is the double displacement reaction. However, this is not what we need, right? So I put this on this slide with the question because really moving forward, what we're looking for is the solubility equilibrium. So what you would have done in grade 11 is switch the partners. So then the calcium goes with the sulfate and the sodium goes with the chlorine on the product side. And you would have used your solubility table to figure out which one was the solid and which one was aqueous. However, that's a grade 11 skill, okay? So now in this case, how is there a shortcut? Do we need to consider the double displacement? And you actually don't. Because you need a KSP value to compare to, then that's what you look for. So the KSP value that's given is always going to be for the solid. And you don't need to write out the double displacement reaction. Okay, we're focused more on this solid and its equilibrium. Okay, so in the blank space next to the question, that's where we're going to start. So we only care about the solid, calcium sulfate. Again, look for the KSP that you're given. You have to be given that, okay? And that is going to be what we split apart. So when you have two solutions, what happens is when you put them together, then the concentration is going to change. And why does it change? Because they're dissolved in water. That's what aqueous by definition means, right? So if you dissolve something in water, that affects the concentration. But then when you put it together with more water, you're going to make it less concentrated or more dilute. So we do need another grade 11 skill in order to figure out what the new dilution will be. Okay, so again, because we only want calcium and sulfate, then we're going to use initially the information from calcium chloride for calcium, and the sodium sulfate will give us the sulfate ions, and they both happen to be 100 milliliters, which is not a requirement, okay? They do not need to be the same. They can be the same concentration, they can be the same volume, but they don't need to be. So then from grade 11, if you remember, when you are diluting solutions and you're figuring out a new concentration, we use C1V1 equals C2V2, okay? So in both cases, we're gonna figure out what the new concentration is once you mix them together, and the new volume in both cases will also be 200. Initially, their concentration is different because you use calcium from calcium chloride and sulfate from sodium sulfate. Why don't we need the sodium and the chlorine? Because they're still ions. They're spectators, right? They come to the event, but they don't participate. They are not a part of the solid. So they're not going to influence whether the equilibrium. They're not going to influence whether we get more calcium sulfate solid produced. Okay, So you do have to, just like this, where we considered what the calcium concentration was and what the sulfate concentration was, the same thing here you need to do, you need to consider each separately. So for calcium, and it doesn't matter which one you do first, right? So this is C1 in the question, 0.1, and 100 milliliters. It actually doesn't matter if you leave it as milliliters or liters. C2, that's what we're looking for, and the volume is V2. So you rearrange and get 0.05. Same thing with sulfate, C1 from the question, V1 from the question, and V2, once you add them together, is 0.2. 0.02 when you divide. So now we have our two concentrations to use for our Q value. So I used this for the calcium and this for the sulfate. When I mix them together with this Q value, how does that compare to the given KSP? So that's why the KSP is so useful. When you're given the KSP, that tells you what kind of Q value you're looking for, so that tells you what kind of ion concentration you need. Okay, so here it is. Here's a weird one, because the number out front here, 3.6 and 1, looks like it should be bigger, but it's not. So if you did this in your calculator might give you this, which is fine. You do not need to use scientific notation, because so -5 means to the left, right? You go 1, 2, 3, 4, 5. Which is quite a few zeros compared to the other one. So when you write it out not as scientific notation, then you can definitely see that Q is bigger than KSP. But again, it's not always going to be possible. Like some of them are 10 to the -11 and stuff. That usually most calculators do not have that kind of display power. So you really kind of have to try your best with the scientific notation. Okay, so Q is much bigger than KSP, so that means that the equilibrium, so if Q is too big, then the products are too big, or the reactants need to get bigger, whatever way you like to think of it. So it has to shift left, and on the left-hand side, every time we do a solubility question will be the solid, so precipitate forms. So Q is greater than KSP. Equilibrium has to shift to the left to increase the R, or the reactant concentration. Let me just see. And to make the Q value smaller, which means a precipitate is going to form. Or you can say that solubility decreases. That is the same thing. Okay. So this type of question is topic number 3, where on the worksheet, where you are going to mix two solutions together. So doing the C1V1 equals C2V2 is an important first step in order to figure out what the new concentration is. So calcium started at 0.1, and then it went down to 0.05 because you're adding more water. So that's going to make it less concentrated when you put the two solutions together. It can't stay the same, okay? So that's an important first step. Okay, so then common ion effect, this is the last one. And like I said, often, arguably kind of the hardest. So what happens when you add a solution that has something that is the same? So it can be soluble. So it could be sodium. It could be, we just did calcium sulfate. So something with calcium, something with sulfate, it has to be the same, because what happens is it basically follows Le Chatelier's principle. You're increasing the concentration of an ion on the product side, and it shifts left, making more precipitate. So again, this is just an application of Le Chatelier's principle. So the fancy definition is that the solubility of a salt is going to be reduced or decreased because it's going to shift away from the ions and make more precipitate. Okay, so if you increase the concentration of the ions, which is on the product side, the common ion is going to stress that side and it's going to shift left to use it up. Okay, so let's do an example, okay? So the solubility of pure lead chromate in water is 4.8 times 10 to the negative 7 moles per liter. So now we're back to the questions where now you're given the solubility. And then it says qualitatively predict how the solubility will change if lead chromate is added to a solution of sodium chromate. And you're given the KSP. So we are going to find the solubility of lead chromate in a solution that contains sodium chromate. So A is is qualitative, so we're going to do qualitative Le Chatelier's principle, and then B is basically proving our answer in A is correct. Okay, so here we have our solid, lead chromate. So how did I know that was the solid? That is the KSP we're given. We're given lead chromate, so that has to be our solid. And then it splits apart into lead ions and chromate ions. And again, if chromate's one of those ones that you struggle with, it is on the back of your periodic table. Okay, you do not need to memorize that. So if we add sodium chromate, then we have two choices. And it will always be two choices, right? In a polyatomic or in an ionic compound, then you have an anion and a cation, or plus and a minus. So it can be either that is the common ion, it doesn't really matter. It's because the ions are on the product side, both of them, then it's going to behave in the same way. So you have lead chromate and you're adding sodium chromate. So where's the common ion? So the chromate ion is, in this case, where the common ion is going to be. So it's going to increase the concentration of chromate because it's a common ion, and then the equilibrium is going to shift left to use it up. If you go to the left, on the left-hand side is always going to be the solid, which means less is dissolving or more precipitate is formed. Okay, so then in part B, we're basically going to be proving that this answer is right. So the solubility should decrease. So what we're given back here, we're given this. Okay, which is sort of looks like it's like more information that we need, really. So we want our answer in B to be smaller than this number. We're just going to compare. We actually are not going to use this number because we don't have lead chromate dissolved in water. So some of the questions in topic 4, they'll ask you to do like, what is the solubility in water, which would be more like the first lesson on this, where the ion concentration is 0, and then it's going to introduce common ions. Okay, so the compound with the common ion will always be 100% soluble. So 100% of it will dissolve. You don't have to worry about, are you given 2 KSP values? It'll always be dissolvable. So the sodium chromate here is 0.01, then the chromate ion is equal to 0.1. And, how are we doing that? Well, we are kind of cheating at Stoic, okay? So when you do stoichiometry, and we don't really do this a lot in grade 11, where we kind of streamline. I'm not going to call it cheat, streamline. Okay, so let's say we have sodium chromate, and we're going to split it apart into sodium and chromate. Okay, so then this, you're given as 0.01, which means that this is also 0.1. Not 0.1, sorry, 1, 0. Okay? Because they're 1 to 1. So again, you could do its coefficient is 1, the 0.10 or molar over 1, right? So you just get 1 to 1. So we're going to do this all the time. So then we needed sodium, which we don't, then you would multiply by 2 because of the coefficient. So these are pretty straightforward. And when you do every single solubility equilibrium expression, like this lead nitrate one, then the coefficient in front of the solid is always 1, right? So then you never have to worry. It's not going to be some other kind of coefficient. So this streamlining process of stoichiometry is always going to work in this case. Oops, sorry. Okay. So you should have lots of, if you printed the note off, you should have lots of space there. I want to do an ice table. So I'm going to go onto a new slide so that I don't have to squish. Okay. Okay. So we have lead chromate is our solid. One more time. How did I know? We're given the KSP for it. Okay. We're going to make lead ions and chromate ions. And normally we would make our ice table and we would put 0, 0. Okay? But we're not going to do that this time. Let me just see if I can get a different color. No. Okay. So now, because I've gone to a new slide, okay, so the stress that we've added is 0.1 chromate. The lead ion is still 0. And then it's going to go up. Okay, and now we're going to solve for x. But here's a problem, because when we solve for x, then if we have a number with the x, like under the chromate column, then we're going to have to use a quadratic formula. And our KSP value is tiny, 2.3 times 10 to the negative 13. So when we try to do the quadratic formula with that, your calculator might actually not even do it. It might make negatives under the root sign and all kinds of crazy things. So what we're going to do is we're going to use something called the 100 rule. Okay, so 100, like the number 100, is 2 decimal places, essentially. Okay, so if you have a number that is 2 decimal places different than the KSP value, then you can basically ignore it. What's going to happen is when we go back and plug in x into this expression down here, the x value is so small that it's not going to change the 0.1. Okay, so I'm going to write that out. If 0.10 is at least 100 times greater than KSP, the value of x in 0.10 plus x is negligible. And what that means is it can be ignored. Okay? So how do you know that? You look at the decimal places. We've got this number can be rewritten 1 times 10 to negative 1, negative 13. That's 12 decimal places different. Many, many more than 2. Okay? So we're going to ignore the x. here. So what you can write is KSP is much, much smaller than 0.10. Therefore, 0.10 plus X is approximately equal to 0.10. Now, lots of times students stress about the 100 rule. Really what's going to happen is you have two possibilities. You have either a common ion in the cation or you have a common ion in the anion. Those are your two possibilities. Whichever one has the common ion, you're just going to ignore the X. Here, we can't ignore this X over here because there's no number with it. So whichever one, it's in this section, the solubility equilibrium section, it is always going to work, the 100 rule, because the solubility, the KSP values are so tiny. Next section, when we do acid-base equilibrium, your textbook will use the 100 rule when I don't even think you should. So it is a very widespread approximation, okay? Because it's just, the X value is just, it's going to be so negligible and small that it's not going to impact the value we get at all. So why complicate the math and then potentially make other mistakes, okay? So we need a KSP expression. So I'm just going to put 0.1 in here and then divide by 0.1. Okay, so that becomes our X value. So what that means is the concentration of lead ions is 2.3 times 10 to the negative 12. Once we add a common ion, and because the coefficient of the lead chromate is also 1, then that value would go in here as well. Okay, so you can test it out. Go in your calculator and put 0.1, like up here with this x1 up here, 0.1 plus 2.3 times 10 to the negative 12. Your calculator will probably just say 0.1. It is going to ignore that X value. It does not influence the size of the number. Okay, so the X is negligible. It is a tiny number, so we can ignore it or forget about it in the 0.1 plus X, so that to make our math lives a little bit easier. Okay, so now we have the solubility of lead chromate in sodium chromate. So now we kind of want to, did we prove our question? So the solubility in water was given as 4.8 times 10 to the negative 7. Is 2.3 times 10 to the negative 12 smaller? It is much smaller, okay? So if the solubility is smaller, that means precipitate forms. So we were correct. Okay, so I'm not going to lie, those common ion questions, they can take a little bit to wrap your mind around. If you didn't do topic 1, don't start with topic 2, go back all the way back. So what we're going to do, this is going to be for Monday, Tuesday, Wednesday, Thursday. On Thursday, I'm going to post a modified lab that we would have done. Obviously, you can't do labs at home. And so I'm going to post that on Thursday or Friday maybe, and then I'll make it due Monday morning. And then next week is just going to be handing that in and review, and then a solubility assignment. Okay, I'm not going to do a big equilibrium assignment, and I really want you to take your time and try to practice these because they are not super easy. And if you have any questions, do your best to try to get them to me, and hopefully I can help. Okay, thank you.